Welcome to the meeting and a very happy new year to you all. I'm Paul Hallett, President-elect of the British Society of Soil Science, and I'm delighted to welcome you all to our first webinar of 2023. Before I welcome our panelists, I would like to introduce the British Society of Soil Science as hosts of today's webinar. So we are an established international membership organization and charity committed to the study of soil in its widest aspects. We have quite a broad membership. We extend beyond a network for academia with a growing membership of practitioners who implement soil science in industry and those with a keen interest in soils. We'll be hosting 10 webinars during 2023, so please do keep an eye out on our website for further details. So before we begin, some basic housekeeping for the webinar today. There are a very large number of people registered for this, so all microphones have been muted. We will be taking questions just at the end of both presentations, and my colleague James, who's an early career researcher, will monitor these for us. So please can you submit any questions that you have by 12:50, and then that'll allow us to get through as many of these as we can. There is a raise hand button. Both speakers have said that they would not mind if people use that, but if you want to use that, go ahead, but probably writing down questions is a better option. And today's presentations have also been awarded BASES and NROSO CPD points. If you're registered with either body, please contact us directly after the event. And finally, please be aware that the recordings today's presentation is being recorded. Okay, so I'd like to welcome the first speaker that we have today, who is Dr. Saran Sohi. So Saran is a senior lecturer in the School of Geosciences at the University of Edinburgh. He's been working on biochar for some time. He co-founded the UK Biochar Research Centre in 2009 after arriving from Rothamsted Research. So his PhD linked the measurement and modeling to describe soil organic matter dynamics. It was undertaken at Rothamsted and supervised at Y. His MSc and BSc studies were also undertaken at the University of London, at Imperial and King's, where his interest in biomass, carbon, and eventually soil originated. He spent a sabbatical year at Cornell, contributed to the International Biochar Initiative as a board member for 6 years, and is currently involved in a number of translational projects, including innovate projects, I should say, and the BAS GGR program. This has brought him back to biochar carbon longevity as the focus for his more basic research. So over to you, Saran.
Thank you very much, Paul. It's a pleasure to have this opportunity to talk with such an important audience about this topic that I've been working on, as Paul outlined, for quite a while now. I'm going to, for those maybe a bit less familiar, and maybe just my personal perspective, I think, on the definition of biochar, talk a bit about the context that I think fits with biochar, and talk a bit about carbon specifically. I want to talk a bit more about context of biochar in agriculture and the use of soils, and I think that leads us on to some areas around how much biochar and where and for what purpose, how biochar functions in soil, and some pointers towards, I suppose, what should happen, in my view, next and where the research might go. So I shall begin. The Biochar Research Centre based in Edinburgh, UK Biochar Research Centre, has a website. I mention that partly because on the front page there is opportunity to click on a button, standard biochars. These were created in Edinburgh some years ago and are now in use over 150 research groups around the world, I think. We do have facilities for making biochar in very controlled and very diverse ways. This is the equipment, the pilot plant that we have on site, which my co-founder, one of the co-founders of the centre, masterminded way back in 2013, and is currently used in many of our more applied projects today.
Saran, sorry to interrupt you. We can't see your presentation at the moment.
Okay. Maybe could you resend the invitation, Chair? Can you send that again? Okay, hang on. Can you resend that so I can use the screen to share? Apologies for that. I think this will momentarily work.
That's brilliant. Thanks, Saran.
I'll just flick back to that previous slide just to highlight the facilities in Edinburgh for making biochar. This is a pilot plant, so if you like, a scalable technology for making biochar in very controlled ways, so we can understand how important the conditions at which biochar is made as to how it functions, and produce a wide variety of very specific types of biochar for different purposes. Right, so yeah, so the word biochar, so I think it was in the room in Philadelphia back in 2006 after the World Soil Congress, where there was a meeting to discuss biochar and its potential, how the research of biochar might be approached. And that also established the International Biochar Initiative. The definitions then of biochar emerged from that, and I think maybe slightly unusually compared with other materials used in soil and around crops. Biochar is defined by, well, I suppose it's in the word really, the source material, biomass, and the process of manufacture, so it's charring or the process of pyrolysis. But the full definition also extends to the purpose of using biochar. Maybe that's also a bit unusual. And there's an aspect here about carbon and an aspect about soil improvement was the word that was used or the term used at the time. But I think, you know, we need to think about crops and soil together. I have a slightly different definition which goes back to the frequently asked question about what is the difference between biochar and charcoal. And I tend to say that, well, biochar is not only made from wood and it's not a fuel, and it has properties that are potentially useful in soil, particularly around production of or growing of crops. And this photo, which Andre, a colleague here, took some years ago, comparing 4 types of feedstock for creating 4 biochars. Now the biochars visually, in terms of their shape, look very much like the starting material. They feel a bit different because the half of the carbon has been stabilized, hydrogen and oxygen have been eliminated. You end up with something that is black, and if you pick it up, it's less dense, and maybe physically its integrity is a bit different from the starting material. But it shows really that you can have many different types of biochar products with many different properties depending on what you start with, which is a good starting point. But what you don't see, maybe visually, but you know is happening chemically at a molecular scale, is that what are predominantly chains with functional groups comprising carbon, oxygen, hydrogen, well, the carbon in the process of pyrolysis is reconfigured into rings. The oxygen and hydrogen is eliminated and the rings join together. You have sheets of aromatic carbon that stack up and create char. Well, soil has aromatic carbon present, and it's the one that we associate with the recalcitrant component of soil, organic carbon. When we put biochar in soil, the organic matter has been pre-stabilized, the carbon has already been put into those forms. So just to hold that as a basic thought. Now, a very important paper from 2010, so quite early on really, Dominic Wolf made this global assessment of the potential of biochar in the context of carbon management, in other words, mitigation of climate change through the efficient stabilization of biomass carbon and its storage in soil. So it's a life cycle analysis. It had some sensitivity analysis of the results, sort of important. But what it shows is that there are globally a number of resources that you might consider potentially available for making biochar. Through this process of pyrolysis in the middle, you create some outputs, you create the biochar, and you create potential energy in the form of, we're sitting here bio-oil, syngas and process heat. Sometimes people talk about pyrolysis liquids, but everything that comes out of a pyrolysis process is in gaseous form. If you don't condense it, if you keep it hot, you have gases that burn and generate heat and can be used to potentially offset fossil fuel use. Then there are the effects on the soil, which is the green part here, in terms of greenhouse gases, where there's the potential to avoid the emission of trace gases, non-CO2 trace gases, nitrous oxide and methane. The potential feedback along the bottom then is the one, I suppose, that's a bit uncertain, in that, you know, if we use biochar tactically and well, there's the opportunity to improve the rate at which net primary productivity occurs, and therefore create some sort of a feedback loop to enhance this. One thing that isn't sort of evident in the life cycle here is the amount. So if we think about this creating 1 billion tons of carbon per year of global mitigation potential, that's 200 kilograms of carbon per hectare of agricultural land globally per year. So that's a small amount, really. In the context of 4 per mil, I think some years ago, at one of the BS Cube meetings in London, I put my hand up because I thought we could do 4 per mil in the very literal sense in the UK, mainly because I was working on biochar, and I think I said, you know, we have potentially 18 million tons of carbon to accumulate, and we have 18 million, just about, hectares of agricultural land. So that's 1 ton of carbon per hectare per year. And I think if there are a few possible ways of getting to that 18 million tons nationally, but I think biochar is probably the only one that could get you there. And we don't have to do the whole ton per hectare per year, but we could actually put a dent in the desire to mitigate carbon at national level using biochar. The stumbling block, of course, is cost. Because this is very different from making compost. You've seen an example of equipment used to make biochar. It's expensive, there's some logistics involved, biomass has a cost. And the third co-founder in Edinburgh for the Research Centre, Simon Hackley, made this analysis early on, and it's really changed my perspective of how I would do my research around the use of biochar. Because if you start with biomass that is fresh, then you're on the right-hand side of this graph and you're looking at numbers for the break-even cost of producing and using biochar that are in hundreds of pounds per tonne. So that's a very different market from compost. It is the case that on the left-hand side of the graph, there are a few that are below the line, sort of pay for themselves, but they are rather small. So I'll come back to that later on, because I think the question of how much biochar is used and for what purposes where is the critical question. But it does lead us to the idea that we might be producing biochar at quite large scale in quite rapid processing. So I put this up as a maybe just to give you a, well, this is large scale, and I don't know if this is necessarily the vision that people would have for the production of biochar, but it might be what's required if biochar is going to be used in agriculture as a standard crop input. So commercial production probably depends on producing a continuous stream of biochar in 20 minutes, and because the rate of throughput and the footprint of that equipment is affected by this, it does favour large scale. And the other thing is temperature. The way to get to the end point of the pyrolysis process and create stable carbon reliably and completely is to use higher temperatures. Lower temperature biochars can be really interesting at the point of production. They're maybe incompletely pyrolyzed, but they may not satisfy an underlying purpose that's about carbon storage. I spent a long time thinking about how we could really understand the relationship between production of biochar and its long-term stability, and then to think about how we could even measure the longevity of biochar in soil on timescales of not just hundreds of years, but thousands of years. And the obvious way was not to put some in soil and watch it, but somehow accelerate time. And through these accelerated aging methods that we developed in Edinburgh and published with Andy Cross, we were able to explore these sort of questions of biochar production in pyrolysis and realize that actually, although the temperature of pyrolysis is a really important factor in terms of how stable, in other words, how long biochar will last in soil, it may not be just the only thing. It comes down to that processing time, the processing conditions, and how quickly you want to make the biochar. And I say that because when we looked at 30 different types of biochar and plotted them on this graph, our measurements of very stable carbon could be obtained with biochar that was made at relatively low temperatures. We call 400 degrees centigrade low. It's true that when you go to very high temperatures, so over 700 degrees, you almost always, mostly there are exceptions, when you go to even higher temperatures, you always get stable carbon. But it's this potential to something a bit different from what you thought at a particular temperature based on your process that should make us really careful in interpreting the literature. So on that topic of literature, there are 21,000 research articles, and meta-analysis has been really useful in helping us synthesize what is essentially very specific work on biochar and to help guide us to what biochar is doing in soil. But a key thing here is really about dosage, and I play around with these sort of cartoons quite a lot in a way of trying to visualize the use of a material like biochar in the landscape. And I've come to realize that it's not going to be applied to soil at 40 tons a hectare as it is in many research experiments, but it will be used as a crop input quite tactically and quite specifically. And when you look at the meta-analyses and this question of, if you like, I tend to say dose rather than application rate, although that might be a bit controversial. I sort of say dose because I think it's the concentration experienced in the soil by the plant that's important, and that depends on where you put it. So in other words, a percentage concentration, which is what's really shown on this graph, might be assumed to be evenly incorporated through the soil profile and across the field. But actually there are other ways to get high concentrations of biochar around roots with low area doses. In other words, if you applied 500 kilograms of carbon in biochar per hectare, but you concentrated it around the plant roots or on the surface of the soil, in some positions in the soil that are important, at the surface or around the roots, you might have very high concentrations and get different very useful effects. And we were sort of onto that quite early because we started to look at what biochar was doing, not in the soil as a whole, but around the rhizosphere. And we started to see that we had an interesting relationship between the dynamics of nitrogen around plant roots and the presence of biochar. I won't go into the details because I realised we're sort of running short on time, but maybe for questions. Biochar, I want to sort of link to how we explore it experimentally, is a complex composite. And what I mean by that is it's got two elements. Maybe it doesn't sound very complex. It's got a carbon element and it's got a mineral element. They're completely different. The mineral element it comes from the starting material. It's pure plant material. It's what we would sometimes call ash, but it's distributed within a carbon matrix that has a very defined structure, a pore structure. And this enables us to create very particular functions in biochar by choosing what we start with and how we manipulate it both before, during, and after pyrolysis, which I'll come to in a second. But we should note, confuses the discussion sometimes. In the process of pyrolysis, you've disconnected the carbon and nitrogen cycles, the carbon and other nutrient cycles, because the behavior of nutrients in biochar associated with biochar does not depend on the biological utilization of the carbon, which is essentially stable. So I tend to talk about short-term benefits of using biochar and long-term impact. And what I mean is that there are ways to get benefits to crop production over the short term by using biochar frequently, probably in small tactical doses, but over the longer term, achieve impact on the soil as a whole, sort of for free. And if we really want to understand those, I'm suggesting that we need to really build on the modelling, because we have lots of observational information and work, but we really need to capture that in models. And I think the key here is that biochar changes in soil over time, and there are, I say here, 4 simultaneous processes because I can't count, and there's actually 5. Leaching, mineralization of carbon, may sound odd because, as I said, biochar is predominantly aromatic carbon. There are traces of condensed, when I say condensed, I mean thermally condensed labile fractions on biochar, very small but very active. Aggregation, this is hardly the incrustation of biochar by other mineral particles, but also facilitating aggregation of biochar and minerals. The fragmentation of biochar doesn't remain as the particles that you add it into the soil over time. In distant time, it's in very, very fine fractions. And then oxidation. And I've highlighted these 2 in purple because I just wanted to touch on those briefly, leaching and oxidation. Oxidation, I think, ultimately is what gives us our measure of carbon storage, and accelerated aging is about oxidation. But in general, the dynamics of each of these is not well described. It's recognised, but it's not well described in models, especially which affects our ability to understand what or predict what will happen at relevant doses on relevant time frames in specific soil types or soil matrices. So just in terms of that manipulation and recognizing those things, these are actually some 3D images that Wilfred Otten created in some of our early exploration of biochar, is to emphasize that you really can change how, well, first of all, you can visualize where the mineral component is. It's the bright spots here in these images, but it's also affected by what you do with the biomass. And if you pellet biomass, you squash it up and you change the way that the pore structure exists. So the pelletized materials on the left-hand side, but then pelleted, a very quite different structure, and thinking about where the minerals go and how they get to the plant is affected. And we've observed these general relationships and just recognize that where you have higher amounts of phosphorus, for example, present in the soil, present in the biochar, its availability tends to increase. And I think that tells you something about both where well, how phosphorus is acquired from the inside of biochar as one of these mineral components, but also how it is distributed within pore structure and interacts with the soil solution. After 15 years of scientific work with biochar, something really important happened. In fact, last year in July 2022, the EU fertilising product regulation, which was created in 2019 to include lots of organic fertilizers. Well, biochar joined the list of fertilizer products in the annex of that regulation, and at least from a wide range of specified starting materials became automatically permissible as a input to crop production across EU member states, but not, of course, in the UK. Now we're not a member state. So I think there's something here that tells us that biochar is being used, can be used, and has value as a crop input, and that we need to think about how we can start making that happen in the UK as well. The carbon longevity topic is coming back because a way of adding value to biochar through greenhouse gas removal is becoming more and more important in terms of the economic calculation. And I talked a bit earlier on about accelerated aging and the prediction of longevity. We really need to understand the 1,000-year longevity of biochar carbon. And we know that charcoal naturally in the environment persists for thousands of years. And that's imperfectly created through wildfire. And yet when we undertake extrapolations, and the diagram here maybe indicates what sort of extrapolation we're doing, when we make these extrapolations from short-term incubations, we end up with much lower numbers. And that's really the reason why I say we need to focus on improving our methods and modelling of longevity. I think we need to start using biochar now, and even require the use of biochar, maybe a bit controversial, but carefully monitor its impacts, because we do know a lot. Talked about longevity, and I've indicated something about integration into fertilizers. Fertilizers are a high value product. Biochar might be expensive to produce, so it needs to integrate with something that already has a high value. And we could think about perennial crops, because if we want to get interactions at the surface or around roots, then that's a good place to start, because you have roots in the ground for longer, and we have twice as much grassland as arable. When we get to the other end of that cost curve that I showed right at the beginning, sewage sludge, lots of problems now in terms of how that might be used on soil in the future, and the process of pyrolysis actually removes many of those. I'll put my conclusions up here. There are only 3, and I'll hand back to Paul.
Great, thank you very much, Saran. That was an excellent talk with a very good broad overview of biochar as well. So just a reminder to everyone, we are taking questions from the question box, so please type in your questions and James will review them for the end of at the end of the meeting. And I'm now going to hand over to Hamish Creber, who's the next speaker. So Hamish is on the cusp of finishing his PhD at the University of Edinburgh in collaboration with Forest Research. He has researched the delivery of phosphorus through biochar application in forest establishment on nutrient-poor soils, and has developed life cycle analysis models for woodland creation. This work has also assessed the potential of biochar in improving seedling resilience to drought stress, and investigated the interaction between biochar and ectomycorrhizal fungi. Hamish is a co-founder of Black Bull Biochar, a company that is scaling biochar use in the dairy sector. And Black Bull Biochar is using tailored biochar products to store carbon and contribute to reducing on-farm emissions and improving nutrient delivery. Over to you, Hamish.
Perfect. Thank you, Paul. Can you see my slides okay?
It's all good.
Yeah, perfect. So yes, thank you for obviously the opportunity to be able to talk to you all today. I've got 2 hats on today. One is my hat as a co-founder of Black Bull Biochar, but also I will be talking about some of my PhD work at the University of Edinburgh. And really what I want to talk to you about is giving a bit more of a focused look of actually what biochar can do in the soil, but also broader kind of how do we design a biochar production through to use system that actually is scalable and actually delivers the potential of biochar, because that's really been one of the big issues of why the biochar industry in the UK is not thriving, as Saran was kind of alluding to and discussing as well. There's this huge body of research that's being done, but obviously that's not really feeding into the industry quick enough to be able to actually unlock the potential of biochar. So in terms of as Black Bull Biochar, where do we come from? So we are a very new startup, and we are funded at the moment through the Bayes Greenhouse Gas Removal Innovation Project, which is looking at piloting different greenhouse gas removal technologies and trying to scale them to be commercial very quickly. And we are kind of paired with the UKRI demonstrator projects as well, which are looking at more of the scientific side of greenhouse gas removal technologies. And for instance, there's a biochar project there as well, whereas we are looking at really testing the commercial system and actually how we can optimize biochar use for the industry and scale quickly. So why is there this real priority to do that now? So obviously everyone's aware that we need to both reduce greenhouse gas emissions but also look at greenhouse gas removal technologies. The real advantage from biochar, though, is that as a land-based greenhouse gas removal technology, it can deliver carbon storage, but also a significant number of other co-benefits, or depending on what your priorities are as a land manager, etc., is actually the co-benefits can be the primary reason for using biochar. So Saran's already introduced really what biochar is. I think the key thing here is that it's an extremely diverse range of products. So biochar isn't necessarily one thing, but it can actually have very different properties depending on what it's made from, how it's made, but also how it's used. And really the trade-off between carbon storage, agronomic impact, or silvicultural impact is fairly complex. So what can biochar do? This kind of image here is how these co-benefits are actually categorized in a hierarchy is both a product of how much evidence there is in the particular benefit, but also the impact can be very dependent on the system. So for instance, carbon sequestration or carbon storage, it's the evidence is there, but also there's potentially less variability in the carbon storage potential of individual biochar products in different soil types, for instance. But things like soil fertility or crop yields, that can be very highly variable depending on what biochar is used and how it's used. So how can we tailor biochar to particular soil functions? And that's really what I was looking at as part of my PhD project. So when biochar is added to the soil, it changes the interaction between both plant soil and biochar, and that interaction is very complex. It's not a simple delivery of nutrients, for instance. Biochar will alter how particularly the rhizosphere responds to biochar, and actually that can have a longer term impact on plant performance. What we can do though is tailor biochar properties to particular soil functions. So whether that's creating a biochar which has got, say, high phosphorus, for instance, or creating a biochar that has a structure which can stimulate root development, for instance. So the image on the right is a SEM image that I took during my PhD, which shows biochar that was added to seedlings, and what we found was that the structure of biochar stimulated root development, but also if we didn't pelletize biochar and retain the cellular structure of the woody feedstock that was made to use biochar, what we actually saw was that hyphae could enter the structure of the biochar to be able to access nutrients within that. And that meant that actually the potential for biochar in terms of providing nutrition for the tree was more than purely for instance, the phosphorus content of the biochar. It was also how accessible were the nutrients that were held within biochar particles. And that's really the key consideration for using biochar is the system designed in a way that it's actually going to perform the function that you're wanting it to have. So I'm just going to quickly now talk about how we can do that, looking at both the woodland creation context, but then also how biochar can be used in the dairy sector as well to provide co-benefits to the farmer, but also greenhouse gas removal. So what we did as part of my PhD in adding biochar to woodland establishment, what we added tailored or specified biochar that was high in native phosphorus content directly to the roots of seedlings during planting, and we were looking at very low dose applications. So what we found was that actually tens of grams of biochar per tree could actually significantly improve seedling growth in the first 2 years following establishment. But what we also saw was, in addition to above ground biomass, that actually root development could be improved through biochar application. So trees that had certain biochars added had larger root systems, and actually once the phosphorus within biochar was exhausted, the larger root systems actually could improve tree resilience, for instance, to drought stress as well. And really the key thing here, because we don't really have time to go too granular into the detail, but it's a much more complicated interaction than for instance fertilizer, which is surface applied, and really understanding how biochar is going to affect crop and the soil is vital. Now in Black Bull Biochar, what we are doing is we are working with Arla to use biochar as an additive to organic fertilizers, so both slurry and farmyard manure. And the reason that we're doing that is to decrease ammonia and nitrous oxide emissions from slurry, but also improve the nutrient retention particularly of nitrogen within organic fertilizers, and then add that to soil. And here what we're really focusing on is the commercialization potential of biochar, so that biochar doesn't just work from a carbon storage perspective, but also it's of value to farmers and land managers from an agronomic perspective as well. The challenge there is obviously the researchers there knowing that biochar can have these benefits, but actually being able to quantify them in a pilot study is crucial to being able to actually commercialize the technology. And that kind of leads me to what are the big barriers to adoption. And there's a few different barriers at each stage of the production process. So one is feedstock. Obviously, producing biochar is tied to the price of feedstock, and the mass loss during pyrolysis means that biochar is always going to produce it is going to be a couple of times at least more expensive than the cost of feedstock per ton. What also is crucial there is sustainably sourced feedstock. So there's quite a lot of discussion in biochar around using waste feedstocks, or whether we use virgin forest products. And there, what we want to do is be able to have quality greenhouse gas removal in biochar. And the only way to do that really is to make sure that we can easily categorize biochar as greenhouse gas removal rather than avoided emissions. And to do that, what we need to do is make sure that sustainably sourced feedstocks used. So for instance, arboricultural arisings, which are not necessarily the carbon's not going to be replaced through replanting, is much harder to actually create quality greenhouse gas removal from a feedstock like that. In terms of production, now there is a number of very high quality pyrolysis producers on the market, but the cost of the technology is still very high. So as more biochar companies come on stream and the pyrolysis technology price comes down, it'll be much more viable for new producers to come on stream and actually make the investment to start producing biochar. And how these machines can actually produce heat for industrial sites is also really important to consider. And then product specification, creating products that actually work and address particular problems, or which are targeted to specific industries, is key to add value to biochar and actually make it cost effective. And then system design and scalability, it needs to be scalable. So there, what we need to do is be able to actually have widespread adoption, not just amongst a very small community of farmers, but actually, or land managers, but actually looking towards wider rollout. And there really, it's making sure that biochar can fit in with existing land management practices and infrastructure. And then lastly, which is really, I think, one of the key things, is how do we monitor, report, and verify the carbon storage, but also the performance of biochar as well, and also overcome biochar regulation hasn't yet caught up to the potential of biochar. So it's how do we create a situation where biochar use can be easily implemented as well. So what do we do as Black Bull Biochar? Well, what we're doing is we're creating a platform where we can link producers and ourselves. We are biochar producers as well with farmers and land users to be able to actually quantify and verify the carbon storage, but also the co-benefits, and create this business to business system. So how does our system work? What we are doing is creating biochar from low value biomass streams, and then the industrial sites or biomass handlers get the heat from pyrolysis. So that's the first benefit. We can produce tailored biochars for specific problems. So at the moment, what we're looking at is creating biochar specific for use in organic fertilizers, working through the certification and quality control of that biochar. And then on the on-farm application side is quantifying and qualifying those co-benefits. So what we can do is we can create high quality carbon storage, but also economical biochar as an economical additive to fertilizer as well to the farmer, so that it's cost effective, which is really crucial. So what can biochar do? I think I've covered the main points already, but it can increase carbon storage in soil, improve resilience to climate change and extreme weather, increase water holding capacity and drainage, improve soil health and nutrient delivery, and then also improve bedding conditions and crop nutrition of organic fertilizers. But again, biochar shouldn't be seen as this kind of one size fits all approach that can do all these things well in every scenario. There's always trade-offs, and it's really crucial to consider optimizing biochar use as well. And then industry as well. So on one side we've got the biochar use, but also pyrolysis to produce biochar for carbon storage is another great opportunity, and does also have commercialization potential as well. So there's a few different aspects to that. One is adding value to low value feedstocks by creating high quality biochars, but also using high quality pyrolysis units allows improved sustainable heat for industrial sites, but it's creating a model where biochar can be produced at scale, but also cost effectively as well. And this is just quickly what we're doing as part of our pilot project is developing a digital platform where we can actually demonstrate, quantify the carbon storage, but also particularly the nutrient delivery of biochar, so that we can then say to farmers, for instance, how much less mineral nitrogen fertilizer they can apply to land through the improved nutritional value of their organic fertilizer. So yeah, I hope that gives you a good background into kind of what we're looking to do, how biochar can be scaled, but also some of the nuances around how the complexity of the biochar use system and how it really needs to be optimized for individual use cases. And yeah, looking forward to taking some questions shortly. And thank you for listening.
All right, thank you very much, Hamish. That was an excellent bridge between the kind of basic science from your PhD and then its application as well. So I'm pleased to welcome James Dowers, who is one of our early career committee members. And he's been looking at the questions that you've been sending in for both the panelists. We've got 15 minutes for discussion, so there's a good chance to talk through things. Please keep submitting them if you haven't done so yet, and we'll try to get through as many of them as possible. If there's time later on, we may also allow people to do raisings of hands and then have some face-to-face questions as well. But I'll pass over to James.
Good afternoon. Thank you for the great questions that have come through. I'll start with Saran. Can you just clarify the energy balance of pyrolysis? Is it net energy out or net energy in?
I realised I glossed over that. I was trying to get back on the topic of soil. Is very important in the life cycle analysis. So for dry feedstock, it's net positive in terms of energy. You're essentially half burning the feedstock or the starting material. So you'd get about half of the energy out as you would if you were completely burning it, with the other half remaining as potential energy in the biochar. It gets more complicated when you're starting off with something that's wet, because extra energy is required to vaporize the water before the pyrolysis reactions occur. On the other hand, steam that's generated in that process does contain energy, it's low-grade heat. But yeah, generally this would work best with well, so I suppose if you want some reference points, pressed sewage sludge works out about energy neutral. In other words, when all the energy that comes out of the pyrolysis process is then required to dry the feedstock. But on a life cycle basis, that's still better than seeing the carbon go back to the atmosphere on the land, because half of it remains stabilized.
Thank you. And Hamish, you mentioned a bit about the interactions with the rhizosphere and a bit about phosphorus content in this as well. But someone's asked that because nitrogen is so important, can biochar supply any N, or is this all lost in the pyrolysis process?
So most of the actual direct delivery of nitrogen native within biochar is most biochars have fairly low nitrogen content because it's lost during pyrolysis. That's where adding it, for instance, with slurry is really good, because actually biochar can absorb nitrogen from the slurry, which would potentially be atmospherically released, and then that's having the delivery of nitrogen. In terms of adding, for what I did in my PhD, adding it in a forestry context into a low nutrient or a nutrient limited soil, what we saw is actually the phosphorus foraging within the biochar meant that the root systems were larger, so actually the accessibility of, they could access more nitrogen in the soil because the ratio between below ground biomass and above ground biomass was higher in biochar treated trees. But actually there was very little direct delivery of nitrogen from the biochar, but there was improved accessibility indirectly through the stimulated root growth and mycorrhizal associations as well.
Okay, yeah. Where's it gone? I just had one. Yeah, so maybe this is a question for both of you. You've spoken about lots of different feedstocks. Is there a conversation to be had around land use? Should we, because lots of farmers are being encouraged to grow trees, should that timber be used, or should we look at waste from the construction industry where wood might be sourced alternatively? So what do you think about that?
I mean, from my perspective, using virgin biomass is critical, really, particularly from a certification and regulatory perspective as well. What we don't want to obviously be doing is using high quality timber to make biochar. So for instance, saw logs. What we want to do is use the lower value the lower value assortments of timber, so whether that be chipwood or whether that's sawmill coal products, and actually being able to potentially divert nutrients and cycle them into low fertility soils is quite a good opportunity, and it does improve that circularity as well.
Yeah, I mean, I agree. I mean, I think in terms of conventional use of organic resources on the farm, I would tend to think that, you know, ultimately straw is a resource for potential resource for making biochar. And if you imagine a situation where currently straw is chopped and incorporated, imagine if half of the straw on average was taken away, pyrolyzed, and then returned to the soil. It would give you a very nice mix of properties useful in soil at the same time as stabilizing half of the carbon in that resource in a pretty permanent way, as opposed to emitting it back to the atmosphere entirely through decomposition. Straw is a resource. As Hamish was saying, in the pasture system where you're growing and feeding grass, straw is not relevant. But you may be in proximity to forestry, increasing industry, and the resource there. Probably nationally, I think Simon Hacker's original analysis suggested that half of the opportunity was in, if you like, waste biomass, and half of it was in fresh biomass. But fresh biomass can be increased, and we could probably be reducing our waste. Waste is heterogeneous. I did mention sludge because I do think that's one. I realise it's not the same in every part of the country, but it is a large definable resource managed in a very particular way already that would be quite amenable to conversion to biochar. But regulation is the barrier at the moment. But I think that is something that we're quite actively working on with with Environment Agency, SEPA, and so on.
And you mentioned briefly in your presentation, Saran, about tactical doses. Can you go into a bit more detail about doses that you're getting at there?
Yeah, so in Hamish's situation, if biochar is being applied to the soil, and what are relatively low area doses, but it's being applied to the surface, the concentration at the roots, or at the surface of the grass is high. So that's a tactical dose, really, because if you want to impact on the roots, then grassland is a good place to go. And the idea that you have to plough biochar into the plough layer and homogeneously distribute it is, I think, a mistake. I would much rather see that it was improving the performance of current fertilizers, or maybe even the creation of smart fertilizers that are applied close to the rows in which arable crops are planted, for example. And also Hamish gave the example of tens of grams of biochar around an individual planted tree. In forestry, the concentrations of biochar around the roots are quite high, but the area dose is, I think it was 200 kilograms a hectare or less.
Thank you. Hamish, can you talk a bit about the products, how many products that Black Ball produce? Are they all produced at the same temperature? And does temperature have an effect on how much biochar is maybe lost in the process? How much is held?
Yes, so there's kind of two questions there. So at the moment, we are producing two different types of biochar. One for application to slurry, which is low density, and obviously has to be compatible with that infrastructure. And then one that can be added to straw bedding and farmyard manure as well, which has to be obviously low dust, higher density, so that they have to have different physical properties. What we're doing is we are producing them under the same temperature, and part of the reason for that is we have a target carbon stability for the greenhouse gas removal potential of the biochar, which is highly linked to pyrolysis temperature. Obviously, higher pyrolysis temperatures, you will have less yield and more energy produced as well. So there is obviously a balance there. But biochar, particularly to be, for instance, EBC, the European Biochar Certificate, that there's minimum specifications and pyrolysis conditions to be able to meet the standards for that, and some of that is linked to carbon stability, which is obviously also linked to pyrolysis temperature as well.
Thank you. So, Saran, sewage sludge can contain a wide range of organic and inorganic contaminants. Is there a risk in releasing some of these to the atmosphere during pyrolysis?
Yeah, I thought the question was going to be about soil, actually. That's something that often comes up. Yeah, so in terms of so everything that doesn't end up in the biochar has to go somewhere. So that would be into the, as I said, the gas stream, the pyrolysis gas that comes out in the processing. So it's how you manage the combustion of those gases to generate the heat, and what's left in the flue gas once you've burned them. So a lot of things, a lot of organic compounds that might be of concern are eliminated in that high temperature combustion of pyrolysis gas, because you can conduct that at 1,000 or 1,200 degrees. Sort of things that then pass out into the flue gas would include some metals and also nitrogen. So we talked about nitrogen earlier, and I often say nitrogen is lost, but actually it's in the flue gas and it can be recovered. But yeah, you would have to manage the flue gas from the pyrolysis gas combustion in the same way as you would in the process of burning, incinerating sewage sludge, or in the normal way, really, in a power plant for any of those trace components. But mainly in the flue gas, it's CO2. You've got the energy out, the heat.
And is there, you spoke about the lifespan of biochar, and the fact, I think you mentioned up to 1,000 years, possibly. Is there a limit to application? Because this audience member is asking about carbon markets, and will it stick around long enough maybe to feed into those?
Yeah, so this is the, I mean, I sort of went through the last slides quite quickly. In terms of greenhouse gas removal technologies, of which biochar is one, the benchmark is 10,000 years, because that's the estimated longevity of carbon sequestered into geological storage after direct air capture, for example. So the market is looking for that 10,000 year stability, rightly or wrongly. Certainly 100 years suddenly does start to seem not long enough in that context. And but I think for that reason we need to demonstrate that biochar does last for thousands of years, and not rely on the conservative analysis of current data that shows with certainty that it lasts, 74% of it lasts for 100 years. That's embedded in the IPCC approach and adopted by Vera and other carbon markets. But as I said, if wildfire charcoal resides in the soil for thousands of years, then we need to show that biochar, how long biochar will actually remain, the carbon in biochar will remain stored in the soil at a much higher level of precision and accuracy.
Thank you. And just quickly, Hamish, from you're working in like the commercial side of things. There was a question about how farmers are usually, or many farmers are usually quick to incorporate stuff that will boost their profits and this sort of thing. Why are we not seeing lots of farmers clamoring for biochar, or are we? I don't know.
I think there's kind of two sides to that. I would say in general, those farmers who do know about biochar are generally very excited and very keen to try it. At the moment, there's obviously supply issues in that it's not really being made at enough scale to be particularly cost effective to them, and also how can we demonstrate that actually it's economical for the farmer? So and that's really where we looking at improving the value of their organic fertilizer, for instance, is because then we can demonstrate that actually it's not just good from an environmental perspective, but it's also cost effective for the farmer. And what we really see is that the biochar can be also complementary to other regenerative agricultural techniques as well. So biochar shouldn't be seen as this kind of individual, put in its individual box. There's also a huge interaction with other both sustainable agriculture and other greenhouse gas removal, land-based greenhouse gas removal methods as well. So there's interest there, but obviously there's still a bit of work to go, really cultivating the agricultural sector for biochar use. But that's obviously what we're looking to do.
Thank you very much for your answers, and I'll hand back to Paul.
Okay, on behalf of the British Society of Soil Science, I'd like to express our thanks to Dr. Saran Sohi and Hamish Creber for coming along to present today, and also to James for coordinating that excellent Q&A session. If you'd like to find out more about biochar, the British Society of Soil Science is developing a guidance note on the topic. If you're not a member of the Society, please sign up to receive any of our newsletters via our website and that's where you'll receive details of when the note is launched in the spring. Thank you for attending. You'll find a quick feedback survey when you leave the webinar, which we hope you will take the time to complete. The recording of this video will also be available after the event on our YouTube channel. Our next webinar will be held on Wednesday, 8th of February, on the topic of microplastics, and is now available for registration via our website, and we will send the link out in our follow-up email. I hope to see you in the future, see you at future events, and in the meantime, thank you again and goodbye.